Calculus, video 75, examples using U substitution. Specifically for indefinite integrals. Again, we'll get to the definite integrals in a few videos from now. So indefinite integrals using U substitution, we take a look at a problem like number 1, the integral of 3x, secant squared, 5x squared dx. Secant squared of 5x squared dx. That looks pretty complicated. Kind of a hint here. If I ever see a trig function, in this case secant squared of 5x squared, for trig functions, if it's ever a secant squared of anything other than just x, then 99% of the time I'm letting u equal whatever that trig function is of. In this case, I'm letting u equal 5x squared. I'm not even really going to look anywhere else except for, oh, it's secant squared of something besides x, therefore u must be 5x squared. Because what I want to be able to do is do the antiderivative of my trig function secant squared, and I don't want to have to worry about doing the antiderivative of secant squared of 5x squared. I just want to be secant squared of u without any other things in there. So for trig functions, almost always we let u be the, let's see, how do we want to say this? The portion of the trig function is of, that's awful. Let u be the, let's just do this. Okay, I can't get the wording right. For trig functions, such as, I'll just say cosine of 8x, I would let u equal 8x. So 1, 2. Such as sine of 3x cubed, I'm going to let u equal 3x cubed. Whatever we're taking the trig function of, that's what I want to let u equal. 99% of the time. Okay. So in this case, that tells us we're going to let u equal 5x squared. And hopefully, when I take the derivative, something there will cancel out with the 3x that I have out front. Du then is equal to 10x dx. Don't forget the dx part of that. Solve for dx, and we get du over 10x. Okay, so we're going to replace the 5x squared with a u, and we're going to replace the dx with du over 10x. And so we get the integral of 3x, that'll just stay there for now. Secant squared of u, we like that. It's just secant squared of one variable, that's it, just u. Times dx, which is du over 10x. And indeed, we see that this x and this x cancel. I have 3 divided by 10. That can come out front as 3/10. Integral secant squared of u du. And we have accomplished the goal of what u substitution is intended, which is creating a much simpler function that I know how to take the integral of. Right? The derivative of tangent is secant squared. Therefore, the antiderivative of secant squared is tangent. And we get 3/10 tangent of u plus c. And then we can go back and replace u with 5x squared for a final answer of 3/10 tangent of 5x squared plus c. And if we wanted to, we could check that to make sure it's right, but it is. All right, next. Number 2. How about the integral of, let's say, 4e to the 8x dx. With exponential functions like e to the x or 3 to the x, right, the same kind of rule applies that I have with trig functions, right? With trig functions, if I see cosine 8x, u is 8x, not thinking much about it. If I see e to the power of 8x, I'm going to let u equal the 8x. I'm going to let u equal the exponent of that function. So, hint, for exponential functions, again, not always, 99% of the time though, we'll let u equal the exponent of the exponential functions. Well, that's probably good enough. For exponential functions, let u be the exponent. In other words, in this case, I am going to let u equal 8x. And the reason is I want to just take the integral of e to the u. I know what the integral of e to the u is. The integral of e to the u is e to the u plus c. That makes it easy. I don't want to do e to the 8x. So we're going to let u equal 8x. Its derivative du is 8 dx. Derivative of 8x is just 8, so 8 dx. Solving for dx, I get du over 8. So now I have, this is equal to the integral of 4. That's going to hang out there. I'm going to replace e to the 8x with e to the u. And then dx becomes du over 8. Okay, I've got 4. I've got divided by 8. That's 1/2. We'll bring the 1/2 out in front. Integral e to the u du. That's terrific. I know the integral of e to the u. It's e to the u. That's 1/2 e to the u plus c. And now I can go back and do 1/2 e to the 8x plus c. You have to be a little bit careful here. A lot of people want to see this e to the 8x and just say that the antiderivative is e to the 8x. But it's really not. The antiderivative of e to the 8x dx is actually 1/8 e to the 8x plus c. Right? If we do the u substitution, we see that right here, right, when we end up taking du divided by 8. Eventually, we'll get pretty good at this, and we'll just know that the integral of e to the 8x dx is 1/8 e to the 8x plus c. And we can see that if we took the derivative, because the derivative of e to the 8x is itself e to the 8x, but then times the derivative of the exponent, which is 8, cancels out with the 1/8, and you just get e to the 8x. Okay, very good. Let's try a third problem. Let's go with, okay, how about, let's make this kind of a double problem. Let's take a look at the integral of 6x over 1 plus x squared dx. Compare that to, so versus, the integral of 6 over 1 plus x squared dx. Okay, two very similar looking things with completely different answers. Let's take a look at the one on the right first. This one here. We already know that. We don't need u substitution on this one. What is the integral of 6 over 1 plus x squared dx? Hopefully we recognize that pattern. That is 6 inverse tangent of x plus c. Remember, the derivative of inverse tangent of x is 1 over 1 plus x squared. Therefore, the antiderivative of 1 over 1 plus x squared is the inverse tangent of x. The 6 comes along for the ride, and we're done. And we see that this answer is an inverse tangent of x, 6 times that plus c. That won't be the case over here. It's not going to be anywhere near an inverse tangent of x for an answer. Instead, in this case, because I have an x in the numerator, we're going to use u substitution. We're going to let u equal that denominator, 1 plus x squared. Its derivative du is 2x dx. Solving for dx, we get du over 2x. Okay? Therefore, we get the integral of 6x 1 plus x squared just becomes u. Dx becomes du over 2x. Dx is cancel. 6 over 2 is 3. Integral 1 over u du. That would be 3 times the natural log of the absolute value of u plus c. That would be 3 times the natural log of the absolute value of u is 1 plus x squared. 1 plus x squared plus c. Again, 1 plus x squared is always positive, so we don't need the absolute values here. And we get this answer. Two very different answers. 6 inverse tangent of x plus c versus 3 natural log of 1 plus x squared plus c. Two very different answers only because this one is 6x over 1 plus x squared, that integral, and the one on the right, 6 over 1 plus x squared. So watch those two, right? Let's do one more. Let's just extend this idea a little bit. All right? What if I had trying to go with an integral to get to an inverse trig function like I have on the right over here, the integral of 6 over 1 plus x squared. But let's start expanding that. What if it wasn't just x squared in that denominator, 1 plus x squared? What if it was 1 plus 9x squared? Could we still get to an inverse tangent? Let's find out. So kind of similarly, 6 over 1 plus 9x squared dx. It still looks like an inverse tangent answer to me. It's 6, not 6x on top. But I don't want this to be, this part right here, this 9x squared, I don't want it to be 9x squared. I need that just to be, x squared, which it's not. So what I'm going to do is, I'm going to try and force that to be just something squared. In this case, I want it to look like this. 6 or some constant over 1 plus u squared. And then I'll do du. So I need to pick a u such that u squared is 9x squared. So what I'm going to do is I'm going to let u equal 3x. Okay, the reason I'm letting u equal 3x is because u squared then is 9x squared. And so I'm replacing the 9x squared with u squared. Right? That creates this 1 plus u squared in my denominator, which is what I want. I want it to just have 1 plus u squared, not 1 plus 9x squared. Okay? To do that, I'm letting u equal 3x. In other words, you're thinking about it like this. You're thinking about it like the integral of 6 over 1 plus 3x, that's being squared. Right? That's kind of what we're thinking, is what thing being squared would give me 9x squared. All right? Doing so, I'm going to let du, then taking the derivative of both sides here, is equal to 3 dx. Dx then is du over 3. So I'm going to replace this. I'm going to have 6 over 1 plus u squared, and then dx becomes du over 3. 6 over 1 plus u squared, because u being 3x, u squared is 9x squared, so 9x squared becomes u, times dx, which is du over 3. 6 over 3 is 2. Integral 1 over 1 plus u squared du. And that is the form for inverse tangent. But this time it's inverse tangent of u. So it's 2 inverse tangent of u plus c. And then we can go back and replace the u with 3x. 2 inverse tangent of 3x plus c. That is using u substitution to get to an inverse trig function. In this case, inverse tangent.